nuclear power. Exactly what is it? What is happening inside of that reactor, aside from making superheroes?
We learned in the 19th century that there's certain elements that we dig out of the ground that are warm when there's no other source of heat going on. So we said, what's going on there? And through the works of Marie Curie and other sort of early Henri Becquerel, and there's some physicists way back then who were the leaders in trying to figure out what these properties are. And they ended up calling it radioactivity.
Radioactivity.
Right. And so when something's radioactive, what it means is there are unstable elements in that substance.
Okay.
And if it's unstable, it means they're actively becoming something else. If you have a heavy element and it naturally then becomes a slightly lighter element, it will give off energy.
Energy.
Yeah, and it'll manifest as heat in that object.
Okay.
Turn of the century, like 1800s to 1900s, people started wondering, well, how much energy is it? Then Einstein writes down E equals mc squared, equating mass and energy. So if you're getting energy out of the atom, where's it coming from? It must be losing mass.
Right.
We were pretty sure you can get energy out of the atom, but we had to sort of develop the physics of that, and quantum physics had to come forward. That was in the 1920s. Quantum physics is the physics of the small, atoms, molecules, that sort of thing. Once that was put into place, oh my gosh, we got something here. And what do you find out? For example, uranium, you can send a neutron. What's the charge on a neutron?
Should be nothing, right?
It's nothing.
Right.
That's where you get the bar joke. Okay?
What's the bar joke?
Neutron goes up to the bar, orders a drink.
Right.
The neutron says, how much? And the bartender says, for you, no charge. What we were deducing through our equations and through experiments was that there's this uranium nucleus. If you hit it with a neutron, and how can you just send a neutron in there? It's got no charge. Neutrons go right through the front door of anything. There's no electrical repulsion or attraction to it. It'll just, I want to go here, I'll go there. I want to go here, I'll go there.
Right.
It marches through the front door of the nucleus of the atom.
All access pass, baby.
All access,
I'm a
backstage.
neutron.
I come with the front, back, side, top, or bottom.
Any door you want.
Okay, so it comes in. If it has enough energy, it can break the uranium atom nucleus into two pieces. And we're pretty sure we knew at the time what two pieces it would be. It would be two other elements. And it would release two neutrons.
Which have the ability to go through any other door they want.
And if you have
then they tell two friends.
And then they
tell two friends.
Yes. Then you have a runaway process.
Man, we got ourselves a reaction.
A reaction. Okay, a chain reaction. Remember, we haven't heard that expression in a while.
Yeah.
Chain reaction. So what you need is enough sort of critical mass of uranium so that when the neutrons go in, and they tell two friends, and they tell two friends, that you get enough neutrons so that every single uranium atom by the end of that gets broken apart. Right. Okay, and this is nuclear fission.
That's right.
Big atoms becoming
breaking
little
apart.
atoms.
So that must produce a tremendous amount of energy.
Oh, yes. Because at the end, you have less mass than when you started.
Right. And
The act of splitting an atom releases energy, and the two pieces have less mass than the one piece that you started with.
So that energy has to go somewhere.
And so now you build a device that concentrates that energy, and you put it in a delivery vessel. That's how every nuclear power plant is making energy today, through nuclear fission. Okay?
Which is breaking apart, becoming smaller, releasing energy.
Right.
In nuclear power plants, the energy released by fission heats up the water surrounding the reactor. This turns the water into steam, which passes through turbines and spins a generator. But if the reaction's not closely regulated, it can overheat, leading to a meltdown, just like what we saw at Fukushima. So how do the control rods slow down the reaction? By absorbing some of the neutrons. The rods are composed of elements like boron, silver, and cadmium that can absorb the neutrons without undergoing fission. If the neutrons have an all-access pass that leads to a chain reaction, well, think of the control rod as a bouncer. Without regulating this chain reaction with control rods, the temperature would keep increasing. With them, we can keep the fission reaction at a temperature we can control.
And so this is the fear factor that people have of nuclear power plants.
Not in my backyard.
You don't want to put it on a fault line or where the thing. You want to sort of protect these things. You could break atoms apart only so far and expect to get energy out of it.
Okay.
Okay? Now put a pin in that.
All right.
At the other end, you have hydrogen, the lightest element. You can fuse hydrogen atoms together and get heavier elements. And that takes heat. So thermonuclear fusion.
Thermonuclear fusion.
Yes.
Right.
So you can bring hydrogen atoms together and make helium. Bring helium together and make carbon, nitrogen, oxygen, silicon. Each of those releases energy as well.
The nuclei of atoms are held together by the strong force, which attracts protons and neutrons together strongly, but only when they get really close together. After the width of a few protons, the attraction falls to zero. Without the strong force, all the protons packed into one small space would repel each other and the stable nuclei could never form. And as they fuse to form larger and larger elements with more protons and neutrons, their nuclei are more stable since they're more bound together by more and more of the strong force. Fusing light elements together makes more stable atoms, releasing the leftover energy. But as the elements get heavier, each additional proton feels a repulsive force from any of the protons that aren't super close. And as we get heavier than iron, the nuclei become less stable. And when they get really big, a tap from a neutron is all they need to break apart into two smaller, more stable elements, releasing a whole lot of energy in the process.
Seems like no matter what you do with an atom, you're going to end up with some energy.
Okay, so it turns out if you fuse iron, it sucks energy out of you.
So it defeats the purpose.
Defeats the purpose.
Right. Gotcha.
Stars undergo fusion.
Right.
And if you have enough mass, it'll go hydrogen to helium. It'll do that in its core, and then and a star is in the business of making energy.
Right.
That's all they know how to do. That's all they do. They get to iron in the core, they try to fuse it, it sucks energy. They try to fizz it, it sucks energy.
Before you know it, that star is just like, what's happening to me? All my energy seems to be going back in on myself.
And then it collapses and it rebounds as a titanic supernova explosion.
Damn you,
It is
iron! Cool. Cool!
You blew it up!
You blew it up! You did it!
Iron is this magic place on the periodic table of elements that is the boundary.
That's it.
Between fission and fusion. Last point.
Go ahead.
Ready?
Go ahead.
I saw a bumper sticker that said no nukes,
No nukes.
and the O in the no was the sun.
Oh, no.
I said, no, you got that wrong. The sun is all about nukes.
Oh, that's all it is.
That's all it's
Just
ever
one
done.
big giant reactor.
That's what that is.
Yeah, we need that.
We need
that. There you go.
Obviously, they want, promote solar energy, but the geek analysis
Right.
says
Wrong choice
Right,
of representation.
iconography.
Look at that. Turns out things didn't get as hectic as I thought they would. Maybe instead of blowing up our world, nuclear power can actually save it.